All right, so the last delineation or differentiation we're going to take a look at when it comes to the different polymers are the categorization as thermoplastic, thermoset, or elastomeric. So in a thermoplastic polymer, what their characteristic is that they soften upon heating, and they also return to their original shape when cooled. Um, So that's their defining characteristic. In contrast to a thermoset polymer, which are also widely used, these are extensively cross-linked. We mentioned this previously. Lots of cross-linking between the different strands, extensively cross-linked. And these do not melt like thermoplastics do. Instead, they tend to char when heated. And some thermoset polymers include the following. We talked about a few of these before, but not the ones we mentioned now. So we have what's the urea formaldehyde polymer. That's used as binder in particle board. For example, it's used as an additive to impart wrinkle resistance to fabrics. We have things like phenol formaldehyde polymers. These are also known as phenolics. These are based on phenol. Those are used in circuit boards, countertops, etc. And then we have melamine formaldehyde polymers, also just called melamines. And these are used as, decorative laminates, kitchen utensils, etc. All of these are examples of, excuse me, thermoset polymers that don't melt typically, but they do char when heated. Elastomeric polymers, as a name maybe suggests, these are lightly cross-linked, so not nearly as many cross-links as there are in a thermoset polymer. Um, these, because of their structure, they can be twisted, they can be compressed, and pulled into different shapes. Yet they return to their original shape when released. So for example, um, well, before we take a look at examples, when you look at the coil, you have a coil strand in something in a thermoplastic elastomer. These, or the coil strands themselves, these are held together by very weak forces. And these are the forces of attraction between the strands themselves. Whereas the strands of a thermoset elastomer are actually held together by covalent bonds. as opposed to just forces of attraction. These are actually chemical bonds, covalent sharing electrons that keep them together. um, you take a look at something like natural latex, for example, which is the basis for things like rubber. Um, Natural latex itself, from the rubber tree, for instance, that's a thermoplastic polymer. It's a isoprene polymer. And again, thermoplastic means that it softens upon heating, returns to the original shape when cooled. And obviously, it's used in a whole host of different applications. Now, um, rubber itself, and where it's used, for example, in tires and stuff, it's not just a natural latex itself, right? It can be altered through a process called vulcanization, which chemically hardens it by cross-linking with sulfur. Right, so you think about latex, usually you think of latex rubber. Well, the rubber itself can be vulcanized to make it harder using sulfur as a cross-linking. So as a result, for example, when you burn vulcanized rubber, you get a bunch of oxides of sulfur being produced that you wouldn't get if you didn't have that sulfur present. So the different things that are added, in this case, the sulfur as a cross-link, does impart some properties to the substance, but it also affects what happens to it when it burns, right? So some of its chemical characteristics as well. And we saw that earlier on too, when we looked at the other types of natural polymers, cellulosic versus protein-based polymers. We saw that the presence of things like nitrogen and sulfur in a polymer does give rise to additional combustion products that you don't find in something that is just made up of carbons, H's, and O's. So that is something that you want to keep in mind, especially as you're looking at a fire scene, what was there, what was being burned. You need to provide extra protection as you're going through in terms of, breathing apparatus, etc., and other things you need to be aware of. All right, so we can take a look at some general characteristics of some of the fire behavior of different polymeric materials. We can sort of summarize just overall what we tend to observe. So the first thing is that linear polymers, so ones that are not branched, for example, have higher densities. We saw this before when we looked at cellulosic materials, for instance, higher densities than branched ones. And that's because they're able to pack or stack close together. And as a result, it leads to lower ignitability and flame spread. What we also tend to see is that thermoplastics, these generally melt upon heating. We also said that cross-linked, so like cross-linked polymers, including thermosets, these require more energy to fragment, to break apart into pieces when heated. And when heated, they irreversibly char. And then the other thing that we saw in lab also this past week when we did our organic compounds experiment, we saw that polymers containing aromatic groups, okay, these tend to suit more readily. So black smoke, black particles soot coming off. These tend to suit more readily than the non-aromatic polymers. You saw this firsthand in lab. And then the last thing, polymers that contain things like bromine, so Br, or chlorine atoms, Cl. These tend to have some degree of fire resistance associated with them. To ignition, fire resistance to ignition by small flames, or degree of resistance to ignition by small flames. So as you are progressing through your classes, taking towards a certificate, you're going to explore in a lot more detail some of the characteristics of, how different substances burn and how they react when they are subjected to flames. We've talked a lot about, polymers generally. We've seen kind of firsthand in the lab how some of these organic compounds are going to combust. These are some general characteristics of specifically now of some of these polymers.